It's okay.
Yeah, Professor, I had a
Yeah.
quick question on the homework for problem. It's problem 4.3b. When it says plot the response y versus each predictor, does that mean like
Yes.
do it one at a time or just like all of them at once?
No, yeah, one at a time. So you take one of the covariates as the variable for the x-axis and the response as the variable for the y-axis.
Okay, thank you.
Okay. Okay, other questions? So let me share my screen and get started. Podcast. Okay, so let's see what we have here. So we started discussing building, let's say, confidence intervals and hypothesis testing. Just to remind you, we are working under a linear regression model, and under the, let's say, the second assumption, which I called E2, the the noise has a multivariate distribution, and so the beta hat, which is the estimate of beta, we calculated its distribution, and the distribution is again a multivariate normal distribution with mean beta and this covariance matrix. Okay, and so this gives us the distribution of every coordinate. So every coordinate is going to be also normally distributed, and the mean is the ith coordinate of the beta, and then the variance would be the ith coordinate of that covariance matrix. And so I've called this VI, and we saw that this variance is dependent on the noise variance sigma squared, which we don't know. So if I ask you, for example, what is the variance of beta hat I, this is the variance of beta hat I. If you don't know sigma, just leave it as is. So sigma squared VI. If you replace sigma squared with s squared, which is our unbiased estimator, you get an estimate of the variance, not the variance itself. And if you take the square root of that estimated variance, you get this so-called standard error, which is an estimate of the standard deviation of beta hat. Okay, and so you can do this for all other estimates. So you can compute the standard deviation of mu hat I, for example, and then replace sigma with s. You get an estimate of that standard deviation, which will be called the standard error of mu hat I. Okay, and so what we started doing was trying to build confidence intervals, and the idea was that we will build it based on these objects called pivots. So a pivot is a function of the observations and unknown parameters whose distribution does not depend on the unknown parameters. So the way we construct this is, in this case, is, as I mentioned, by doing this standardization of beta, beta hat I. So you subtract the mean, divide by the standard deviation, which is sigma root vi. And from this result, because we know that beta hat I is distributed like normal, which means beta I, and variance sigma squared vi, from this we conclude that z has standard normal distribution. And then I went through this argument, which I'm not going to repeat because it will take some time. But if you have questions, feel free to ask. So what we end up, so this is going to be a pivot because the distribution here does not depend on normal, sorry, on unknown parameters of the model. But there's a sigma which we want to get rid of. And so what we do is we multiply by sigma over s. So if I multiply by sigma over s, effectively multiply by sigma here, and then divide by s, so I get rid of sigma and replace it with s. So what we end up having here is I end up with basically this guy. So that's going to be my new statistic. And this new statistic does not depend on any unknown parameter besides beta I, which is good because I want to build a confidence interval for beta I. And if you do this calculation, you end up with, so you do a little bit of manipulation, you end up with this form, which is saying that I can write t as z divided by root of u divided by n minus 2 plus 1. So u here is this guy, and this we talked about before. So this has a chi-squared distribution with n minus 2 plus 1 degrees of freedom. So, and we argue that this u is independent of z because u is a function of the residual vector, and the residual vector is independent of beta hat I, and basically z is a function of beta hat I. Okay. So the reason for this is u is a function of e, and z is a function of beta hat, and e is independent of beta hat. Okay, that's a little argument there. Okay. And so because they're independent, this construction, this is the construction, the definition of a t random variable. So this random variable t that we have constructed has a t distribution with n minus t plus 1 degrees of freedom. Okay, so that was what we did last time. So any question about this? So this was the conclusion last time, that t, which is this guy, has a distribution which is t with this many degrees of freedom. Questions? No questions. Okay. So let's use this information. So we have a statistic. So t is a pivot. Is also a pivot. And the only unknown parameter in it is the beta I, so we can use it to build a confidence interval for beta I. So the next question is, what is a confidence interval? So how many people know what a confidence interval is? Yes, no, in the participants window. Let's not show them what I'm not going to show what confidence interval is. So, okay, yes, a couple of yeses. The rest of the people probably aren't sure. So one of you who knows, okay. One of you who knows, maybe want to say what a confidence interval is. It's one of the tricky things in statistics. And what is a confidence interval?
It's a measure of like how confident you are that a prediction or like a value is within like a certain range of values.
Right, but that's like the intuitive explanation. But what is a mathematical definition? Like a precise mathematical definition. That's what we want to have. But let's say within the framework of probability, how can we make it precise?
The probability that it lies between two values of a distribution, or actually
It's what is it?
that that like a number.
So right, we have to make it more precise. So it's close, but you have to make it a little bit. Anyone can make it more precise?
I think it's based on our observation and our estimate of the parameter, the likelihood of the outcome we observe. So
The
like
likelihood of the outcome that you observe.
based on the model we have.
So let's be specific. Let's say I want to build a confidence interval for beta I. So you build a confidence interval for an unknown parameter. Okay, so beta I don't observe. So I want to know beta I. So I have an estimate of beta I, which is beta hat I, and I want to get a confidence interval. Confidence interval is like an upgrade of an estimate. It has more information. So what would be a confidence interval for beta I? Can you maybe say that what you wanted to say in terms of this example, beta I? What would you expect the confidence interval be? Okay, let me give you the definition that I like, and it's a precise mathematical definition which sort of dispenses with ambiguities. Let's say, if you want to, you can,
Professor.
like in words, if you want to state things a little bit difficult, but this is a precise statement. So confidence interval, let's say,
Professor, I
yes.
think you have quit the screen share.
Oh, really?
Yeah.
Oh, okay. This is strange. Okay. Can you see it now?
Yeah.
Yes. Okay. So this is the definition. So let's say, so you said an alpha. So alpha usually for us is 0.05. So this thing would be, let's say, a 95% confidence interval. For a scalar parameter beta I is a random interval. Okay, is a random interval. Let me clear this. So usually, so it's a random interval. The key is that it's a random interval such that beta I lies in this random interval with a certain high probability. Okay, or the interval contains beta I. So the key is that the confidence interval is a random interval. Just like beta hat I is an estimate, and it's a random variable, the confidence interval is a random interval, which means that there are these two endpoints that are random variables. So each of these things is a random variable. And beta I is not random, but you can compute the probability under your model that beta I lies in this random interval. And that probability turns out, let's say, to be, if it turns out to be 1 minus alpha, then we say that I hat is a confidence, like 1 minus alpha, 100 times minus alpha percent confidence interval. So if this is like 0.05, this is divided to 0.95, then you would say that this is a 95% confidence interval. Okay, so with 95% probability, beta I lies in this random interval. Okay, so this is called the confidence interval level 1 minus alpha. And the frequentist interpretation is that the frequentist interpretation of probability is this. So if you run the experiment many times, say n, and each time you observe a realization of this random interval, so at the ith experiment you observe I hat I, then you can approximate this probability. So this probability you can approximate with this. So this is the fraction of the experiments that in which beta I belongs to I hat I. So this notation is going to be 1. This is the indicator. 1 if beta I belongs to I hat I. That's the meaning of the notation. So 0 otherwise. So this summation is counting how many of the intervals contain beta I, and then I divide by 1 over n. So it's like how many number of I hat I that contain. It's actually bad notation because I just realized I should have called this something else because I is there. So let's say this is J. Let's do it with J. I want this to be J because beta hat I is fixed. So then this is the number of I hat J that contain beta I divided by n. Okay, so if I repeat the experiment, each time my random interval takes a particular value. And I see, if I know beta I can see whether it lies in that interval or not. And then I compute how many of these intervals in n experiments contain that, and then divide by n. So this would approximately be 1 minus alpha if you subscribe to the frequentist interpretation of probability. So in other words, roughly 1 minus alpha times n out of these n intervals contain beta I. Okay, does that make sense to people? That's what a confidence interval is. Okay. So what happens is that for a given data set, you obtain a deterministic realization of the confidence interval. And for that particular one, you cannot say necessarily contains beta I or not. Okay. None of these realizations you can say for sure that beta I is in there. But what the statistics or frequentist statistics is telling you is that if you repeat it many, many times, let's say a majority of these intervals, 1 minus alpha, fraction of them would contain the truth. Okay, that's the meaning of a confidence interval. Does that make sense to people? Hello? Questions?
So can you say like based on the observation of your experiment, there's like 1 minus alpha probability that the true beta I is within this range.
Right, so you can say, so based on the observation, it's, so the probability is a little bit beyond observation. So the probability tells you what happens if you like repeat the experiment infinitely many times, basically. Okay, so the probability tells you what happens for the ensemble of all the experiments on this problem that you run. For a given particular experiment, for a given data set, for a given realization, there's nothing that you can say. But if you repeat the experiment many, many times, that's the meaning of the problem, the frequentist meaning of the problem. Then you can say that this many out of n would contain the truth. Or you can say the probability that the true value lies in this random interval is 1 minus alpha. That's the easiest way of saying it. That's like within the framework of probability. But what does it mean to say the probability that beta I belongs to I hat is I minus alpha? That's one way of interpreting that statement. But yes, you can say that the true parameter lies in the random interval with probability 1 minus alpha. Then you have a confidence interval of the 1 minus alpha.
Thank you.
No problem. Other questions? Okay, so now the next couple of slides are a little bit, I would say, do a simple thing the hard way. So I'm gonna do it the simple way. So let's try. So so this is supposed to be after, unfortunately. So read the confidence interval first, then we come here. and build a confidence interval for beta I based on the t, which is just beta hat I minus beta I divided by, I'm going to write it at the standard error of beta hat I. Remember? So this thing is also the standard error of beta hat I over from here. So the t statistic basically is beta hat I minus beta I divided by the standard error of beta hat I. And we showed that this guy has distribution Tn minus b plus 1. Okay, that's what we showed last time. Okay, now what I would like to do is, I know the distribution of this t. So I'm going to go, and this distribution is symmetric. It looks like a normal distribution, but it has heavier tails. So it looks like this. Okay, so, and what I would like to say, so this is going to be centered at beta I. Okay. The mean is going to be, sorry, the mean is going to be 0. This is 0. So it's going to be 0. But okay, so what we have here is, I want to basically find a two-sided interval. So I'm going to try to find a number, let's say call this, I'm going to call this, let's say tau, such that the probability that this is bigger than tau is 1 minus alpha. Okay. And you can see, I mean, you'll see why this is interesting. So because this is symmetric, so this interval, this translates to this part.
Professor?
Yes.
So should it be, should the right side be alpha instead of 1 minus alpha?
Right, yeah, right. So I want the interval that contains, so this is, okay. So I want, right. So I'm gonna let this to be alpha. Because then if this is true, then I have the probability that t belongs to minus t and t is 1 minus alpha. Okay.
Professor?
Yes.
So, should the test statistic itself be an absolute value, or it can be a negative value, the t?
So t can take both positive and negative values. So t is like distributed like a normal. That's the distribution. So this is the
So
distribution. It takes positive and negative value.
Oh,
Right,
so
the
it
center.
doesn't have to be the unpositive.
Sorry?
So it's not necessary has to be
Yes,
the.
no, t is not necessarily positive.
Thank you.
It looks like a normal distribution, but the tails are a bit heavier. Right, just like a normal distribution centered at 0, it can take positive and negative values with equal probability. This is the same. So what I would do is, I would build, I want an interval which is, let's say, centered around 0 here. And I'm going to find that tau, and you can go and compute it from t tables, basically. So what this tau is basically the place such that this is, because there's symmetry. So if I make the area under this curve to be alpha over 2, so this is the probability. This probability is basically the area under the density that I so highlighted. Okay, so that's the that's how you compute the density. So this is basically integral. Let's say ft of t dt. over the interval, which is negative infinity to t, negative t, and t to infinity. So if I integrate this function over this these two intervals, that would give me, if I integrate the density, that would give me that probability. And by symmetry, I just want this area to be alpha over 2, then this area would be alpha over 2. The sum of the two areas would be alpha over 2, and the sum of the area in between would be 1 minus alpha, because the total area has to be 1. So this area would be 1 minus alpha. Those two areas would be alpha over 2. Okay, and so what I need to basically, so choose tau such that the probability that, let's say, t is bigger than t is alpha over 2, or equivalently, the probability that t is less than tau is 1 minus alpha over 2. Okay, so this is a tau that satisfies this is called the 1 minus alpha over 2 quantile of the distribution. Sorry, this, okay. This is strange. Let me try. Okay, sorry, I have to close this. Okay. So this tau you can compute from a t-table. So once we have that tau, then I know that the probability. So this would be this is called d1 minus alpha over 2 quantile of t n minus p plus 1. That's the distribution. So now what I would do is I'm going to expand. So expand this. So I know that the probability that t is in negative tau, and tau is 1 minus alpha from this part. And so this is tau. And I also know that this is beta hat I minus beta I divided by standard error of beta hat I. Okay. So if you do the manipulation, so if you do some algebra, you can see that this is equivalent to beta I being between beta hat I plus tau times the standard error of beta hat I, and beta hat I minus let me call this gamma. I think I've called this gamma, like about this two things, like so tau SE beta hat I. This is like tau times standard. Okay, so that if you plug this in here, and then if you do some algebra, you get that this is equivalent to what I've written here, and so this is going to be 1 minus alpha. And you can see this you can take as b hat in the definition of the confidence interval. This says I hat. So I would have the probability that beta I belongs to I hat is 1 minus alpha, where I hat is just this interval, beta hat I minus tau standard error of beta hat I, and beta hat I plus tau standard error of beta hat I. Okay. Does that make sense to people? So that would be the confidence interval based on this T distribution. Questions? Let me rename this tau while you think about this. I'm going to call this gamma because later I called this gamma. So let's do this. Gamma everywhere. Gamma. Choose gamma such that this holds. Yes, and then gamma here. Gamma there. Gamma would be here. And this gamma is not dependent on the parameters of the problem besides the n and t plus 1, okay, and alpha. So the way to compute this is that you go and look at the t table and you figure out what gamma you need to choose such that the probability that the t distribution with this many degrees of freedom lies below that level is 1 minus alpha over 2. Okay. Questions? Do you have any questions? No questions? It was really obvious to people, yes? I'm going to assume that this was okay. So this is basically the same idea, and you can see that's the interval. And sometimes we write it just simply as, I might write it as beta hat I plus minus gamma times the standard error of beta hat I. And this should be I. Okay. So this is a little bit about quantile function, which I'm gonna just briefly mention and skip in the interest of time. So the quantile function is the inverse of the how to choose. That's the how to choose gamma. The quantile function is the inverse to the CDF. So this is the CDF, the probability that t is less than x, and the inverse of the CDF is called the quantile function. So it's f minus 1, and it has this property that if I evaluate f at f minus 1 of p, I get back p. If you unpack this, this means the probability that t is less than f minus 1 p is equal to p. Just use the definition. So use this definition here. So this is the definition of an inverse of a function. And if you combine it with this, you'd get that. Okay. And so you can see your gamma here would be, so the gamma that we want is gamma would be f minus 1 of 1 minus alpha over 2. So if I take p to be 1 minus alpha over 2, I get 1 minus alpha over 2 here. And so the gamma would be the quantile function evaluated 1 minus alpha over 2. And sometimes we write this as if this is a t distribution, I write this quantile as td of p. T distribution with d degrees of freedom. So so for example, we write something like gamma is t n minus p plus 1 of 1 minus alpha over 2. This is just the quanta 1 minus alpha over 2 quantile of the distribution. So the notation is not that important. You just have to understand what it is. Okay. It's good to know what a quantile function is, but if you don't know, it's fine. So you can still just work with this idea here. This should be obvious. Okay, questions? Comments? Okay, so let's see an example then. This is the same idea, so I can write just this as the 1 minus alpha over 2 quantile of the t distribution. And so here's an example. It's in your book. I haven't included the background. It's something about I think probably something about the properties of a hook or something like that. I forgot. but it's a regression problem with sample size n equal 4 and p equal 1. So it's a simple regression problem, and we have an intercept in the model. With an intercept in the model with an intercept. So p plus 1 is going to be 2. And we have sort of fitted the model, and we have the beta hat 1 and the standard error beta hat 1. So we calculated these, which you should be able to calculate as you've done in the whole problem. And we want to find a 95% confidence interval. So this would be 1 minus 0.05 over 2. That's 1 minus alpha over 2. Alpha is 0.05. And the degrees of freedom here is n minus p plus 1, which is 14 minus 2, which is 12. So I'm going to go and look up the t-table for this quantile, and it turns out to be 2.18. So my confidence interval would be basically minus 1.266, that's beta hat 1, plus minus 2.18 times 0.034. Okay, that's the standard error. And so this gives you a confidence interval, which evaluates to this thing. Okay. And so what this is saying is that we can say that, let's say, beta 1 is in this interval with confidence 95%. It doesn't mean that with probably 95% beta 1 belongs to this interval. Okay, that's not. Because if you repeat the experiment, you get a different value of beta hat 1, and you get a different value of the standard error. And you repeat it another time, you get a different interval, you get it another time. So what this is saying is that 95% of those intervals contain beta I. This is one of them, okay? It's a tricky interpretation, but that's sort of, that's what a confidence interval is. Does that make sense? Calculation is okay with people? Hello? Question? Okay, yes. One yes. Okay, good. I'll let you think a little bit, see if there's any questions. So most people probably have seen how to compute confidence intervals. Hopefully now you understand where it does come from. So the way it comes from is we started from this derivation. So we know this distribution for beta at I. And from this we drive the pivot, which is this guy, and this has Tn minus P minus 1 as is this distribution. And then we can, because we know quantiles are this, we can try to make this T lie in a certain interval with certain probability. And that's what you do here. So make sure that T lies, if I want to make sure that T lies in interval centered around 0 with probability 1 minus alpha, I'm going to choose gamma such that that happens. And that gamma would be a quantile, would be this quantile of the T distribution. And then what we have is that you replace T with the expression that we have here, and you end up with, after some algebra, you end up with your confidence interval. Okay, so the probability that beta I belongs to that random interval. You can see again, the key is that beta I lies in this random interval. So you're not building a confidence interval for beta hat I, you're building the confidence interval for beta I, but based on beta hat I. Okay, so the confidence interval is for beta I, but the confidence interval is constructed based on, it's actually centered at beta hat I, and the length, so the length centered at beta hat I, or point estimate of beta I has length 2 gamma standard error of beta hat I. So you can see if the standard error of beta hat I is small, then the confidence interval is small, so you have a more, let's say, accurate estimate, hopefully. And if a standard error of beta hat I is big, then the length of this interval is big, so you have a more uncertain estimate. So you can't say for sure beta hat I is a good estimate. Okay? And questions? Okay, and you can use confidence intervals to do hypothesis tests. We're going to talk about hypothesis testing shortly, but here, let's say I want to test, assume we want to test the null hypothesis of or the null hypothesis H naught being beta I equals 0. I want to test whether beta I is 0 or not. One approach is to let's say at level, you test at a certain level, at level alpha. Okay, so at level alpha means I want to have the type 1 error probability be at most alpha. What it means is that under the null distribution where beta I is 0, I want to reject the null at most alpha % of the time, at most 5% of the time. So 95% of the time I want to keep the null, do not reject. And you can argue it's not difficult to see that this is equivalent to test, so you can divide. So we can define a test statistic that does this based on I hat, which is just beta hat I plus minus gamma standard error beta hat I. So in this interval, if you look at this interval, we say that, so reject H naught if if 0 does not belong to this interval. Okay, if 0 does not belong to this interval, reject the null, otherwise accept the null. Or some people don't like to say accept the null, but do not reject the null. And you can verify that if your confidence interval is at level alpha, then this test will have significance level alpha, which means that type 1 error will be at most alpha. This you can show if you've taken 100B. You should be able to do that. So in this problem, for example, if you agree with this test, do we reject, let's say we want to test whether beta 1 is 0 or not. Should we reject in this example, or should we not reject? Should I reject the null that beta 1 is 0?
This interval does not include 0 or reject. Yes,
so if you use this test, because it doesn't include 0, you reject at level like 5%. So if you build a confidence interval with at level like a 95% confidence interval, and if the value that you're testing is not in that interval, you can reject the null hypothesis that beta is equal to that value, and that would have level, that test would have level alpha. Okay, just see whether the interval contains that number, and decide whether to reject or not. Okay, questions? So there is a bit of argument here that this in fact has the desired property, that the significance of type 1 error would be alpha, at most alpha, but I'm not going to argue that. You could argue it for yourself. But anyways, so let's move on in the interest of time to the idea of doing hypothesis testing. We just did a little bit of it, so you can use confidence intervals. And in fact, what I'm going to talk about is equivalence to the confidence interval approach. But let's do it anyways. So suppose you want to test, hopefully people know what hypothesis testing is. That's one of the basic problems in statistics. I have a null hypothesis, which usually looks like something like this. I have a hypothesis about the regression coefficients. For example, I want to I have a guess that beta I is 0. I want to test whether that's true or not. So beta I being 0 means the ith covariate does not. So means the ith covariate does not influence or affect the response. So I want to test whether that is true or not. And so the alternative would be that beta I is non-zero. Okay, so how do we do this? So we have an estimate beta hat I, and if beta hat I is close to 0, then our guess is that probably beta I would be maybe 0. And so we do not reject. And if beta I is far from 0, then we're under the alternative, so we reject. This makes sense because beta hat I is unbiased for beta I. So if beta I is 0, then beta hat I is going to hover around 0. If it was biased, then this doesn't make much sense because beta I being 0 maybe means beta hat I is close to 2. Then that's not good. But because it's unbiased, beta hat I is going to hover around 0. But the issue is that we need a sense of a scale. So how big beta hat I should be before we reject. And so that's the main issue with hypothesis testing. So let's say I build a test that rejects based on the magnitude of beta hat I. So if the absolute value of beta hat I is large, I reject it. If not, I just want to quantify how large I need to be, or beta hat I needs to be. Beta hat I, the scale of it would depend on the problem. So better choice would be to divide by the standard error. So the standard error is an estimate of the standard deviation. And so this is sort of a standardization. So we know that beta hat I is close to 0. And if we divide by the standard error, which is like the standard deviation, we hope that things are more or less normalized. And in fact, in this problem, we can see that if we do that, beta hat I divided by standard error would have a t n minus p minus 1 distributions under the null, okay, based on what we have done before. So why is that? Anyone? Why is this statement true? So the null hypothesis is beta I is equal to 0. That's the null hypothesis. So why, if beta I is equal to 0, then beta hat I divided by standard error of beta hat I has a t distribution with that many degrees of freedom?
Because then beta hat I minus beta I is just beta hat I. Then divided
Exactly.
by standard error, we got t distribution.
Right. So this we just showed that beta hat I minus beta I divided by standard error. This has a t distribution. In this case, this part is just 0. So that is equal to 0 under the null, under H naught. And so we get this result. Okay. Under the alternative, this is not true, but under the null, beta I is 0, and so we have good. Okay, so so if you want to do it at a certain significance level, this is going to be equivalent to the competent interval construction. But now that I have this, this will be all test statistics. So we're going to base our test based on this. So what I can do is that I know that this under the null is a t-distributed variable. I can go and see how extreme this is for a t-distribution. Okay, so I know that, for example, the distribution of this is, again, something like that. So that's the distribution of, so this is 0. Okay, so this is the distribution of beta hat I distribution. Beta hat I divided by the standard error of beta hat I. And if I observe a certain value, so in an experiment, I observe a value, for example, here, then this is more or less likely for this distribution. Okay, you would expect this to happen. But if I observe in an experiment, I compute this, and it turns out that U is in fact here. So this is a likely value. This U here, if U is there, this is unlikely. Maybe, okay, or far in the tail. So what I can do is to see whether it's likely or not, I'm gonna, so let's say observe this value turns out to be U. I'm gonna compute the probability that this T is statistic. This is gonna, let's call this T. This is a T distributed variable. The probability that this random variable absolute value is bigger than U. I'm gonna compute that probability. I'm gonna call that a p-value. Okay, so if this guy is very small, then I'm in this tail of the distribution, and so I'm gonna reject. If this is not small, I'm somewhere here. I'm sorry. I need you somewhere here. Then I do not reject. Okay. So what this is saying is that go and see. So this notation here means under the null. So we look at the distribution of T under the null and evaluate this event. What is the chance that the absolute value of T is bigger than U? Where U is the realized value of the T statistic. And that will give us a number, and this number is more or less called the p-value. There is a better definition of the p-value, but it's the realization of the p-value, basically. So it's the realized value of the p-value in this problem. And if this p-value is small, let's say generally you do it less than 0.05, then it's unlikely that the observed value has come from the null hypothesis, and then you reject. So if you set it to be, so your test would be, so reject if p is less than 0.05. So this test is going to be equivalent, in fact, to this test that rejects if 0 does not belong to I hat, as long as this is a, let's say, 95% confidence interval. So whatever significance level you want, if you build the associated confidence interval and you do the test this way, or you compute the p-value and reject if the p-value is less than alpha, you should get the same answer. This you can sort of prove for yourself if you want. But the advantage of the p-value is that it contains more information. It's not just a given threshold. So, for example, if p is 0.01, you reject. And if it's like 10 to the negative 4, you still reject. But 10 to the negative 4 gives you more information as to the unlikeliness of the event. So it's more unlikely that you're under the null. If it's like 10 to the negative 15, it's really a significant effect, at least from the statistical perspective. Okay, so the p-value has more information. So let me write this here. Reject if p is less than 0.05 is equivalent to reject if 0 does not belong to I hat, where I hat is the 95% confidence interval or beta I. Okay, so these two procedures are equivalent. But the p-value contains more info. So I hope you got that. I'm not going to write it. It's just you're truncating the p-value at a certain threshold, but the p-value itself has more information. Like it could be like much below the threshold or very close to the threshold. That gives you some more information. Okay. Questions? Let me do an example and then you can think of questions. Maybe it becomes more clear. So again, back to our example, this was the confidence interval that we built. Now if you want to do the p-value approach, so first that 0 does not belong to this interval, so we should reject the null at level 5%. But alternatively, we can compute the p-value. So in order to compute the p-value, you're going to compute the realized value of this t statistic, which is going to be just the absolute value of this beta hat divided by the standard error. Okay, so that's this guy. So you just evaluate that, and so you get 37. Okay, that's the value of the t statistic. And then you go and see what is the chance that a t distribution with 12 degrees of freedom, that's the random variable, in absolute value is bigger than 37. And you can do it in R, or you can look at the tables. And it turns out that this probability is very small. This is like 10 to the negative, like 8.58 times 10 to the negative 14, which is definitely much less than 0.05. So you would reject. But you can see that this has more information. 0.05 is much bigger than 10 to the negative 15 or negative 14. And so you guess that probably you're going to be fine. You're more than significant. Okay, much more. Okay. So these are the two approaches. It should give you the same answer. Questions, comments? So maybe I should ask you, I'm going to ask you a question. So what is a p-value? I've talked about the p-value, but just like confidence interval, it's one of those tricky concepts in statistics. It's worth trying to figure out again and again. So what is a p-value? Anyone? You guys checked out? Anyone still here? Just give me some explanation. It doesn't have to be accurate. What do you think of a p-value?
I think p-value is the outcome is at least as extreme as what we observe.
Right. Okay. So your statement lacks the what is the starting phrase? So the outcome is as extreme as that. What is there more to it? Is it? Can you finish a complete sentence?
So the probability that the outcome is at least as extreme as the one we observed.
Okay, yeah, that's a good definition. That's
Can I
I
say
would say
my?
that. Go ahead. You want to say something? Go ahead.
I think p-value is something let us to be sure when we reject H0 null hypothesis. As how many percent we are sure we reject H0 when exactly H0 is run.
Right. Sometimes people say it's your degree of surprise or how, again, confident you are, how sure you are. So these are good heuristic explanation. What Shushin, I guess, mentioned is a little bit more precise. But if you really want to understand what a p-value is from a mathematical perspective, you need to be a little bit more precise. And I'm going to do it here. I don't expect you to necessarily, this is like an aside, but because people have asked this question, and I also have controversies, p-value controversies, papers on the web page if you want to read. Once in a while, it's like statisticians fight over whether p-values are good, what they are, and apply the statistician especially or in other fields. From time to time, so they write articles that p-value testing is sort of flawed, you shouldn't do it. P-values or hacking. There are other sort of a lot of things that like jargon that sort of floats around and you hear it. Here is like a mathematical statistics perspective of p-values. They're very precise objects, and if you understand them, you'll have a problem like entering the debate. And they're neither bad nor good. So you just have to understand what they are. And just like confidence interval, it's usually confusing. So this is the precise definition. This is one precise definition. The p-value is just a random variable. Okay, and this random variable is just a transformation of your test statistic. It is neither a probability nor anything else. It's just another random variable which you get by transforming the original test statistics. Here is my test statistic t, and my claim is that the p-value is another test statistic which you get by a certain normalization of this. And the way this normalization works is that it brings that test statistic on the scale of probability. So you can now compare it to probabilities. So this t cannot be compared to probabilities because it's just not related to probabilities, but you can bring it on the scale of 0, 1 somehow, such that when you compare it to probabilities, then it makes sense. That's the idea. So again, it's a transformation of your test statistics, so it's a random variable. So how to define it precisely? It goes like this. So suppose t is your like our random variable that has t distribution. That's our basically test statistic. And then I define this p of u to be the probability that this absolute value of t is bigger than u. So this is related to the CDF. So for example, you can compute this. This function is basically related to the CDF. So the CDF would be, the CDF computes this probability, and P of U computes this probability. Okay, it's just the alternative to the CDF. Computes that area. So that's P of U as a function. So I have this function. And then, so this is a deterministic function. You can compute it for any value of u, you get a number. And then I apply this function to my t statistic, which is beta hat I divided by SE divided by beta hat. So this is my test statistic. I apply this function. And so this gives us a new random variable because this inside is random. I'm putting it inside this function. The result is going to be random. And so this new random variable is called the p-value. And it's a one-to-one transformation of the test statistic. And I can recover the test statistic by inverting this map. And so I'm not losing information. And the advantage is that it brings it on the scale of the type 1 error probability. So what it means is that this is defined, or this construction allows me to say that the probability under the null that p hat is less than alpha is equal to alpha. So if I reject at level alpha, this test that rejects at level alpha is going to exactly have type 1 error probability alpha. That's the advantage of it. And the reason why this is true is because you can show that under the null, once you do this transformation, as an exercise, you can show that p hat under the null would have a uniform distribution. Okay, under this transformation, p hat will have a uniform distribution, and what is the chance that uniform 0, 1? What is the chance that a uniform distribution on 0, 1? So if I have a uniform distribution, that's my density. Sorry, that's not the density. This would be the density. So 0 here, 1 here, 0 elsewhere. So what is the chance that I observe a value which is less than alpha? So that would be the area here, which is just going to be alpha. So the probability that p hat under the null is less than or equal to alpha is going to be alpha. And that's the advantage. So I can just construct the test by saying that I reject whenever alpha is less than, whenever p hat is less than alpha, and that would give me a test at level alpha. Okay, this simplifies your life because the threshold on the original test statistic, beta hat I divided by the standard error of beta hat I, is not this simple. I can't compare this to alpha and say I reject whenever this is bigger than or less than alpha and then expect the test to have level alpha, but I can do it with p-value. This p-value sort of normalizes the experiment. No matter what the experiment is, this p hat is going to have a uniform distribution under the null. And so you would have a test of level alpha if you reject at level alpha. Okay, so that was my quick, precise explanation of the p-value. Did that make sense to people? So p-values are not probabilities. They're like random transformation. The transformation of your original test statistic, but they're on the scale of probability. You can compare them to probability to reject, and then you'd get a test of low, certain low. So that's a more precise state. Okay, does that make sense? Do people understand this more or less, or? So for example, if you understand this, if you compute the p-value and you see that it's like 0.5, you reject the test at level 0.05. But you can't say the null is correct with probability 0.5. That doesn't make sense, okay? So under the null, it's equally likely to observe 0.5 or 0.01 or 10 to the negative 4. All of these values are equally likely, okay? It's equally likely under the null to observe 0.9 for the p-value or 0.0001, let's say. Okay, it's uniform. So it's a little bit mentally, you have to prepare yourself that the p-value makes sense again in the frequentist sense. So if you repeat this experiment many, many times, okay, you observe different p-values. The p-value is random variable. You observe different p-values under the null. If you repeat the experiment under the null, in each experiment, if you look at the p-value and you compare it to alpha, and equal how many times the p-value would be less than or equal to alpha, it's going to be like the fraction would be alpha. So alpha times n of the experiments, in alpha times n of the experiments, the p-value will be less than alpha. And in the rest would be bigger than alpha under the null. Okay. So again, a particular specific p-value in a specific experiment doesn't tell you anything about whether the null is correct, whatever. So there's nothing to be stated. But if you consistently reject using this rule and if you repeat the experiment many times, then you can make sure that your type 1 error probability is bounded by alpha. Okay, I tried to, did my best to try to convey what p-values are. And we're almost out of time, so I'm gonna just stop here and then let you ask questions. This is an important topic. Maybe we can pause a little bit. We have like 2 minutes. If it's not clear, let me know and we'll go over it again.
So can you explain again why P is uniform distributed?
I can assign this as a homework problem. This you can prove. Prove for yourself. So I know that this guy, this is T, okay, and has a T n minus T minus 1 distribution under null, okay?
Oh,
And then I have constructed this object, this guy, to be like basically something like the complementary CDF, two-sided CDF of that distribution. So let me give you a simpler example. This is similar to what is called probability transformation. Again, this probability transformation. Similar to. So suppose x is a random variable with CDF f of x, i.e. probability that x is less than or equal to x is f of x. Okay, define a new random variable u by applying f to x. This is not f of y to random x. Let me write this like this so it's not confused. This x is, say, t. U. Let's write it as u for all u in R. And then apply this f to capital X. So this is a new random variable. Then show that u will have a uniform distribution as an exercise. Okay. So hint, or so assume, we need to assume that f is continuous, hence has an inverse, f minus 1. So you have an inverse, okay? So I can write x as f inverse u. Okay, use this fact, so exercise. So if you understand this, then you can also do the other one. Okay, does that make sense? Have you seen this before? No? Shushan, did you ask you asked the question, right? Does that make sense? Or
yeah, I've seen this before.
okay, so go over this and then try to prove that yourself, that p hat in this case is uniform under the limit. Okay, so we're out of time. I'm gonna post these and you can take a look, and if you have questions, let me know either in the office hours or next time we can go over them. So we have almost completed the hypothesis, and there is a little bit about the confidence interval for the regression function and prediction intervals, and I'm going to talk about them next time. But so far, you should have most of almost all the things that you need for doing the homework problems. Okay, so we've catched up to homeworks. Okay, thank you, and see you on Wednesday. Sorry, Monday, hopefully. Thank you. Bye-bye.